Okay, in this lesson we're going to start our new unit on similarity, and we're going to focus on similar figures, in particular triangles today. So the objective, students will define similarity and find the missing sides in similar figures. So let's define what we mean by similar figures. So similar figures are objects that have the same shape but not necessarily the same size. They can be rotated, they can be flipped, they can be translated, but the general shape stays the same. Now they can have the same size because congruent figures are automatically similar to each other, but normally one is going to be bigger than the other. We have a symbol for similarity, and that symbol is the tilde. So it's like the top of the congruent symbol without the equal part. So for example, to use that symbol, I could say triangle ABC is similar to triangle DEF. That means they are the same shape, but they are not necessarily the same size. So we're going to highlight a couple of properties in similar figures. So the first thing that's important to know is that in similar figures, corresponding angles are equal. The angle measurement doesn't change because, again, the shape stays the same. And if the shape stays the same, the angle measurements have to stay the same. So that's just like our congruent shapes. Again, corresponding angles are still going to be equal to each other. The difference is in the corresponding sides. They are not necessarily equal anymore. We say corresponding sides are in proportion. That means they would have the same ratio. Every set of corresponding sides would create the same fraction when you reduce them. And so there's a different way of solving for these. And just to show you what I mean by corresponding, if I have triangle ABC, and I'm going to say it's similar to triangle DEF. So I say triangle ABC. If I'm given that triangle ABC is similar to triangle DEF, that does not mean they're congruent. DEF looks bigger. I can write 6 things about this. I can say that corresponding angles are congruent. So if I marked it up, I know angle A and angle D, because of the correspondence here, A goes with D, B goes with E, C goes with F, just like congruence. A and D, B and E, C and F. But I can't put the tick marks in for the sides because they are not the same length. So here are some statements I can write. Angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Okay, just like we do with congruent triangles. But the sides being in proportion look like this. The length of AB over the length of DE. That is the ratio of AB over DE. Okay? That ratio is equal to BC over EF, which is equal to CA over FD. So we have to make sure we go in the same order. If I start with AB, I have to start with BC and CA. So if AB is on the top, so is BC, so is CA, if I'm going from one to the other. If I start with DE, if DE is on the bottom, then so is EF and FD. Now you can also compare ratios within triangles. I could say AB over BC is equal to DE over EF. But usually we are going in between triangles. So we're mainly focusing today on finding missing sides when you have a pair of similar triangles. And there's a couple steps to write down. You're going to set up a proportion. Usually you're given enough information where you have two measurements on one triangle, one measurement on the other, and you're trying to find the missing side. Sometimes you have the scale factor instead of two measurements. Either way, you're going to set up a proportion, and that means a fraction equal to a fraction, or a ratio equal to a ratio. And then to solve a proportion, you cross multiply. Most students are really familiar with cross multiplying. I'm going to give you some fancy terms here because this is geometry. If I have a proportion, A over B is equal to C over D. We have some names for these four letters here. The two that are on the lower left and upper right, those are called the means. Okay, each one is a mean. And the other two are called the extremes. So we have means and extremes. So the fancy way, we have a fancy way of describing cross multiplication, which we're going to need later on when we do similar triangle proof. So I'm going to tell it to you now, and then it'll come back up later on in the year. So here is the statement that we will use later on. The product of the means equals the product of the extremes. And that's basically cross multiplying. If I multiplied A times D, it would be equal to C times B. So now we're going to work through some examples of how you would use this with similar triangles. In this example, I have ABC is similar to DEF, so that is given. And we want to find ED. So if you look at this, I have length AB is 21, BC is 7, EF is 3. Some of these things you might be able to do in your head, but we're still going to follow through with the work. And I'm trying to find ED. If I just set up the proportion, I like to put what I'm trying to find in the upper left, ED. And if I'm looking at ED, and I look at my correspondence, and visually you can see ED is going to go with AB. So or BA. ED over BA, it really doesn't matter which way you put the letters, is equal to, and then I use the two sides that I know, EF over BC. So that's EF over BC. Okay, that's the proportion you would use. Now I just substitute things in. I have X over 21 is equal to 3 over 7. Cross multiply, and you get 7x is equal to 63, and x is equal to 9. So in the end, ED is going to be 9. You could also look at it just intuitively. 7 times 3 is 21, so 3 times 3 is going to be 9. If you looked at a scale factor between the two, that would be a little bit trickier, actually, because it would be 3 over 7 if you wanted to use a scale factor. But we'll talk about, as you can see it actually right here. So the scale factor, this is what I'm trying to get to. When you have a ratio that's reduced of corresponding sides, that results in a scale factor. So that's what we could call this side. The scale factor between the two. One more note on this, and you'll be seeing this quite a bit. This is the bigger triangle, this is the smaller triangle. So the scale factor here is 3 over 7, and which would make sense because I'm going from big to little. And it's always end over beginning. So from big to little, and that's why the scale factor is 3 over 7 instead of 7 over 3. Okay, in our next example, we're told that the triangles are similar, but we're not given the correspondence. So we have to think about this a little bit. I have all three sides of triangle ABC, and I've got to match them up with the triangle DEF. Okay, that doesn't mean that necessarily that A corresponds with D. When you do a problem like this, you're going to look at the lengths of the sides. Okay, and then you're going to look at the scale of the picture. I know sometimes we have to say the drawings are not to scale, but here you got to kind of look at it and see. So if I look at this guy, the side that's missing is the shortest side. Okay? So that's the one I need. Well, if I look over at my original triangle, the shortest side is going to be 6. So x is going to go with 6. If I wrote this out in letters, which you don't necessarily have to do, FE is going to go with BC. Okay? Then I look at my other two, and it doesn't matter which one you choose. If I choose the longest side here is 12, and the longest side over here is 18. So I could do that. I could say DE goes with AC. And that's enough to, that's sufficient to substitute in and find your answer. So if I say x over 6 is equal to 12 over 18. Smallest over smallest, biggest over biggest. Small triangle, big triangle. Small triangle, big triangle. So you have to have consistency when you set up the proportion. All right, if I cross multiply, I get 18x is 72, and it looks like x is going to be 4, which should make sense because that should be the smallest number, and 4 is the smallest number. So sometimes we have ratios in a problem, and the problem here is actually much smaller than what it takes to write it out. Two similar triangles have a ratio of 2 to 5, so this can be the scale factor when you get there. If the larger triangle has a base length of 15, find the length of the corresponding side of the smaller triangle. So I don't necessarily, I don't have any lengths of the smaller triangle, but I have a scale factor between them. So if I look at that 2 to 15, 2 to 5. See, even in videos I mess up. 2 to 5. Well, the 2 has to go with the smaller triangle because it's the smaller number. The 5 has to go with the larger triangle. Okay? So you can use this as a ratio in your proportion. 2 over 5 is equal to, I'm trying to find the smaller side, so that goes with the 2, and the larger side is 15. Okay, even though I don't have the lengths of the smaller sides, I have the scale factor between them, and you can use that in the proportion. Anytime you see a ratio, you can write it like a fraction. Okay, so now I cross multiply, and I get 5x is 30, so x is 6. Finally, we can also have a ratio just within a single triangle. The side lengths of a triangle are in the ratio of 2 to 3 to 4. Those are not the lengths of the sides, it's the ratio of the sides. And the perimeter is 108. Find the length of all 3 sides. So when you have a problem like this, we don't really use it as a scale factor this time. We have to write an equation, okay? We know the formula for the perimeter of a triangle is you add up all 3 sides. So if I draw a triangle, I know the perimeter is 108. When I have a ratio like this, all you're going to do is put an x next to each number. So 2x, 3x, 4x. That's how you represent the 3 sides. And then you just add them up. 2x plus 3x plus 4x is equal to 108. So that's 9. 9x is 108. And x is 12. Now I want to find the length of all 3 sides, so we take our 12 and we go back and substitute it in. So 12 times 2 is 24. 12 times 3 is 36. 12 times 4 is 48. And if you add those up, they should all add up to 108. So those are several different types of examples that you'll be expected to do in your homework, all using similarity and ratios.